Hello, everyone. My name is Malik Muqdadi, and my presentation is on interfacing an embedded wireless sensor network for monitoring the temperature of coal gasifiers. Now, a brief overview of coal gasification is it is a process of producing synthetic gas using coal, water, air, and oxygen sometimes through intense heating. This produced synthetic gas is way more efficient for generating electricity when compared to natural gas. However, the byproducts do cause degradation of the gasifier, which is a furnace composed of specially made ceramic blocks which can withstand the intense heating required for the process. And so in order to prevent the degradation of these refractory bricks, smart bricks were embedded sensors within them were designed to monitor the internal temperature of the furnace, as seen up here. And so the goal was to establish a sensing circuit which could pick up the input of this embedded sensor within the smart brick and wirelessly transmit that to a computer base station in order for us to monitor. And so for the first step of this, we had to pick up the input within the embedded sensor inside the smart brick. So the sensor chosen was a thermally sensitive resistance output. This allowed us to give the brick a resistance which changed with temperature. It was a inversely proportional relationship, which meant that as temperature increased, the resistance of the brick decreased and vice versa. And so this allowed us to develop a very simple resistive sensing circuit using only a Wheatstone bridge and two operational amplifiers. Let me make this a little bigger. And so here we connect the smart brick as R times 1 plus delta. And using this circuit, it allows us to convert this resistance to a voltage value, an output value that is connected to an Arduino Nano 33IoT, which is a microcontroller that supports low energy Bluetooth. And so it digitizes this data and sends it over to the base station for monitoring. With low energy Bluetooth, we also add in a real-time clock circuit that allows us to modulate the intervals at which this Arduino stays on for. It also allows us to control how long we keep the Arduino on for, allowing us to really decrease the amount of power and minimize the amount of power consumption that we have. And so for our results, we were able to prototype the circuit with our Arduino on a breadboard. However, due to the RTC chip still not shipping in, we were unable to prototype that. We were able to run a few test runs, and they were successfully able to output the correct values that we aimed for. And so for their first test run, let me make this a little bigger, we connected the sensing circuit to a variable resistor known as a potentiometer. And as we increase and decrease the value of the resistor and the potentiometer, as we see here, the output value or the measured value of the base station also increases along with it. And so we knew that the circuit successfully was able to pick up these resistance values and went on to testing it with a smart refractory brick. This test was also successful. As we see here, we see an inversely proportional relationship, as here's when the temperature increased, and whenever it cooled down, the resistance values started to go up again. When compared with the resistance values measured by a multimeter, these values were very close and indicated a successful run. And so really the main focus here then becomes on power consumption, as we want this to be portable and as low as power consumption and run as long as we can have it. And so for comparison, this resistive sensing circuit really only pulled a current within the microamp range. We compare currents because it has a direct correlation with power consumption. Now, looking at the low energy Bluetooth support from the Arduino Nano, we see at 4.5 volts, we pull a current of 41 milliamps, over 1,000 times that amount that's pulled from the resistive sensing circuit. And so with the inclusion of an RTC circuit, we hypothesize that this will drop down to single digits milliamps, really lengthening the time at which this can run. And so to conclude our work, breadboard implementation was prototyped and created, and it accurately ran and displayed the correct values that we were looking for and accurately monitored the temperature of the furnace. And so future works include prototyping the RTC circuit, implementing and prototyping batteries for portability, multiplexing a multitude of Wheatstone bridges for increased range and precision, soon, and fabricating a printed circuit board for compactability of the system. I would like to acknowledge the National Energy Technology Laboratory, the Department of Energy for funding this project. Special thanks to them. Thank you.